All right, hopefully the last video for the packet. Talking about solubility, now things dissolving in other words, so solids dissolving to make solutions. Okay, now there's a picture of a cup of tea, and I think I've told you this example before when we talked about saturated solutions. Talk about my brother, right? So my brother back in the day used to have 13 sugars in his cup of tea, and you get to about 6 and then no more dissolves, and that's a saturated solution, right? Fair enough. Now you can pretty much make a saturated solution about anything. You get to the point where it doesn't dissolve anymore. Fair enough, right? So we talked about saturated solutions before. For sugar, you can actually dissolve quite a lot of stuff in there. Salt, table salt, lots of stuff dissolves before it gets saturated. But what about things like chalk? If you look in solubility charts and things like that, chalk is insoluble. Silver chloride, classic, insoluble, right? But no, remember everything's in equilibrium. Remember, there is no such thing as a non-reaction or a complete reaction. Everything's in equilibrium. It's just that this is dissolved to such a small an extent, we hardly ever bother with it, right? But if we do want to bother with it, we get into this equilibrium math we're going to talk about now, okay? So things that are apparently insoluble, like chalk, are actually what we call sparingly soluble. A little tiny amount goes into solution. So if I had some calcium carbonate, put it in a beaker with some water, I'd have a small amount of calcium and a small amount of carbonate go into solution and then get into an equilibrium, right? Even though the amount is tiny, it does reach a maximum amount, a small yet limiting amount, right? So at that point, it's technically a saturated solution. So it's saturated with a very low concentration of ions in solution. Okay, so because they're in equilibrium, and at that point of saturation, it's kind of a fixed number, constant time, right? So the equilibrium constant is calcium carbonate. That's my 2 ions in solution. If I'm doing this technically in terms of formulas and things, divided by the calcium carbonate. Now, if you remember from the good old days when we did heterogeneous equilibrium, these guys have measurable concentrations. And this is a solid, it does not, right? So we can say, hey, K times calcium carbonate concentration equals a new constant, which we call solubility product, which equals calcium 2 plus carbonate minus. Okay, so same kind of thing. We're going to kind of multiply the constants out, and we get what's called a solubility constant. Okay, it's just basically the ions in solutions, because the solid doesn't count in any equilibrium expression. Okay, it doesn't have a measurable concentration. So any sparingly soluble salt ionic compound will have a relevant or related KSP. Okay, numbers are always small. All right, remember the line in the sand for solubility. Well, sorry, let me back up. The line in the sand for a reaction or not reaction was 10 to the minus 6, right? Okay, think of that as an equilibrium number, right? So here we've got 10 to the minus 9. Yeah, it's 1,000 times less than the threshold for a reaction. It happens, just not in very large amounts at all. Okay, so it is a measurable but small amount. It's called a solubility product because it's this one times this one, a product, and what's called solubility, which we'll get to later, is technically defined as the concentration of the metal ion in solution. Okay, so this times this, solubility product, and it's a fixed number, it's a constant. All right, so since we are dealing with sparingly soluble materials, okay, the KSPs are necessarily low. Okay, now you may you may recognize a couple of things which we in Chemistry 101 defined as insoluble. In our solubility chart, AgCl was defined as a solid. Why? Because its KSP is super small, right? On the other hand, Ag2SO4 was designed as soluble. Its KSP is above that -6 threshold, right? So that was aqueous before, and that was a solid before. But remember, that's all relative. They all dissolve to some degree as defined by the KSP. All right? The smaller the KSP, the less they dissolve. All right? So we can write solubility expressions for these things. just like we did with the calcium carbonate. All right, so it's always a good idea to write the equilibrium first. Barium +2, sulfate -2. In equilibrium, Ba2 plus SO4 2-. You know, there it is right there. So we actually have a value we can stick on in a minute. Therefore, KSP, products over reactants, reactants we forget about, which equals that number, 5.0 times 10 to the -9. Okay, nice place to pause. Pause, give the remainder a go. Okay, remember this is careful with these because they have more than one ion. Okay, so give it a pause, give it a go, and I'll catch you up. All right, next one, calcium fluoride in equilibrium with calcium ions and 2 fluoride ions. Careful, we're gonna have that whole power thing. So KSP, products over reactants, forget about the products because they're solid. One of those, same rules apply. Same rules apply. All right, which equals a number 3.9 times 10 minus 11. All right. Finally, silver sulfate, Ag2SO4. Careful, 2Ag plus, SO4 2-. Ag plus squared, SO4 2-, which equals a number, it's 2 Ags. -5, below the -6 threshold, so we generally say, you know, before, oh, that's soluble, but it's very, very sparingly soluble. Okay, so as with other equilibria, we raise the concentration to the power of the stoichiometric constant. Okay. So hopefully writing those is not so bad. Okay, they are mathematical relationships, so we can do some interesting math. Okay, so try this by yourself. Okay, hopefully you can work it through given the, let me just give you the expression here. It's the one we saw earlier. So an easier one to start, just 2 things dissolving, and the number was 4.96 times 10 to the -9 from previously. Okay, so question says, you drop a stick of chalk, calcium carbonate. Now this is a heterogeneous equilibrium, so the chalk has to go in before the equilibrium can establish, of course. Okay, then it gets into a saturated solution with low concentrations. Okay, that's the KSP situation. Okay, so you drop a stick of chalk into some water. What will the concentration of calcium ions be in the resulting saturated solution? Okay, after we got to equilibrium. Okay, so equilibrium establishes when we got saturation. All right, so let's think about it. Since 4.96 times 10 to the -9 equals Ca2 plus times CO3 2-. And because this is in a 1-to-1 ratio, concentration of this guy, we call it X, is the concentration of that guy because it's in a 1-to-1 ratio, right? We don't know how much goes into the solution, all right? So therefore, this number equals X squared. 4.96 times 10 to the -9 equals X squared. Therefore, X equals the square root of 4.96 times 10 minus 9. 6.7 times 10 to the -5. Okay. So again, it's a... Could we do a grid for this? We could, but it's at the point now where, you know, there's no reactant, so the grid isn't really necessary. Okay. Now, we get interesting questions when we combine pH with sparingly soluble materials. All right. So let's look at this one. Okay, now it's a harder example, and I do like to put this on tests, hint, hint, right? Okay, so we have magnesium hydroxide, MgOH2 solid. It's going to get into solution, right? Now be careful, because you're going to get Mg2 plus 2OH minus, right? There's 2 in there. Okay, now because we've got OH, that we can get to POH and then pH, right? Okay, so this one, a saturated solution of magnesium hydroxide has a pH 10.17. If we think about it, we get one of these and two of these through the dissociation, right? So if that's X, that's 2X, right? Okay, now if you've got pH, we can go to POH. If we've got POH, we can find the OH minus ion concentration. And because that divided by 2 is the magnesium, we can find the magnesium ion concentration. Okay, so saturated solution of magnesium hydroxide has a pH of this. Find KSP. KSP is going to be what? Be careful. KSP equals magnesium times hydroxide squared. Careful, which equals X times 2X squared, 4X cubed. All right, so KSP is 4X cubed. So solve for X and then 4X cubed. All right, pause there, try it. Okay, and then I'll do it. Okay, so pH plus POH equals 14, therefore POH equals 14 minus 10.17, which equals 3.83. Therefore, OH, do that reverse math, 10 to the minus POH, 10 to the minus 3.83, 1.48 times 10 to the minus 4. Okay, so that's OH minus ion concentration, divide by 2, therefore, to find X, which equals 1.48 times 10 to the minus 4 over 2, 7.4 times 10 to the minus 5, therefore, KSP 4x cubed equals 4 times 7.4 times 10 minus 5 cubed. 1.62. Oh, sorry, bring it up. 1.62 10 to the minus 12. All right, so it's a tiny number, but you expect tiny numbers for solubility products, don't you? Okay. All right, so given the pH of a sparingly soluble salt that features an OH minus ion, you can find KSP. Okay, and that's a favorite for tests, so beware of that. Okay. Now, as I mentioned, solubility is generally speaking the concentration of the metal only. Okay, so the solubility of any sparingly salt is expressed in terms of the metal ion. This comes from industry, because in an industry they're always interested in separating out these ions, you know, and then making the metal. So you might pull out some sodium, some silver. Sorry, you wouldn't pull out sodium; that would be too soluble. Silver, lead, things like that. So when you're refining metals, which generally have compounds of low solubility, this is super important. Okay, so solubility, which we just call it S, equals the concentration of the metal ion. Okay, and in this case, because it's 1 to 1, it's also the concentration of the counter ion. Okay, so if you want KSP in terms of S, it's nice and easy, very simple. Okay, so KSP equals, this is S times same number S. Oh, I'm just doing it again, right? Okay. KSP, solubility of silver times the same number, solubility of silver again, because it's the same number, 1 to 1, which equals S squared. So therefore, if you want solubility by itself, it's just the square root of KSP. All right. Now, that gets a little complicated when we look at things with multiple products, for example, okay? So determine KSP and solubility expressions for the following, okay? So here, solubility of the metal is S, so that, because there's two of them, is 2S, right? So therefore, KSP equals calcium 2 plus fluoride minus squared, because there's two of them, which equals S, and that's 2S, and that's squared, which is 4S cubed. Okay, so KSP 4S cubed. All right. If I rearrange all that, make S the subject, you can do this by yourself. S is KSP over 4 cube rooted. All right. Next one. What's the calcium fluoride solubility? Okay. S, in other words. Okay. And let's do this. So when we look at this one, okay, what's the solubility? That's S. That's the concentration of calcium. Okay. So when it says that, we're really solving for the concentration of calcium. Okay. Find S, it's the concentration of calcium from KSP. So when we think about it, we're just going to use that equation. S equals the cube root of KSP over 4. Well, that's easy, right? 3.9 times 10 to the minus 11 over 4 cube root, which equals 2.1 times 10 to the minus 4 molar. Okay, fair enough. That wasn't so bad. Now, so that's the solubility of calcium, right? Calcium ions. Okay. Now, in industry, they don't usually do things in moles per liter. That's what we do in chemistry, okay? So in the biochemical and the industrial fields, it's usually grams per liter or milligrams per milliliter, okay? So how do we turn this into what they want, okay? Grams per liter. All right, it's actually simpler than you think. If you remember back to Chemistry 101 and we did that ppm calculation, very similar, right? Okay, so 2.1 times 10 to the minus 4 moles per liter, and we're going to turn that into grams per liter. So all we're doing is turning moles to grams, right? How do you turn moles to grams? Well, you multiply by molecular weight. What's the molecular weight of calcium fluoride? It's actually 78.1 grams per mole. Okay, so (1.6 times 10 to the minus 2 grams per liter. Okay, so be careful there. Okay, think about a chain conversion. It's a bit like a ppm conversion. Okay, and this is more popular in fields such as, you know, industrial chemistry and biomedicine and things like that. All right. Next one, you can apply, of course, common ion to this. It is an equilibrium. Okay, so you can throw a common ion in and you get what's called selective precipitation, which is super important in industry. All right, so it's kind of a tricky one to get the hang of, but once you do, it's pretty straightforward. Okay, so we can modify the solubility of a specific ion in a mixture by playing with this math, okay? And then, hey, we can selectively precipitate it from a mixture if that's the case, all right? So, calculate the molar solubility of calcium fluoride. So really, it's the concentration of calcium 2 plus in a solution that's 0.1 calcium nitrate. So remember, all nitrates are soluble. So I'm going to have a 0.01 calcium ion as a, yeah, you guessed it, common ion, right? So I'm going to use a modified ICE grid. So that's the trick. So I'm going to use a modified grid, okay? This is how it works, okay? We're going to throw a little pellet of calcium fluoride into a beaker that's already calcium 2 plus aqueous in solution at 0.01 strength, okay? And then an equilibrium will set up between the calcium fluoride and the solution, but the amount of calcium going into solution will be diminished because it's going to be competing against, if you wish, the calcium that's already there. Okay, so let's look at this. So calcium fluoride, equilibrium with calcium 2 plus 2F minus. Okay, I, C, E. Initially, obviously it's a solid, doesn't really apply. This is the common ion, and initially none. Change, we're going to make, normally we write an X here, don't we? Normally we write an X here. But hey, in terms of our algebra, it's an S, isn't it? And that's 2S. Alright, at equilibrium, we have 0.010 plus S and 2S. Alright. You can make the weak acid approximation. That's an even smaller concentration, right? Okay. So, KSP, don't lose sight of our prize here, right? Calculate molar solubility, that's S. Yeah. Okay. So KSP equals calcium 2 plus fluoride minus squared, which equals approximately 0.01 times 2S squared, KSP. Should have the number somewhere. Okay, oh yeah, it's in the previous table. Flip back, it's in the table. We got it, there it is. Okay, so basically we're going to solve for S, yeah? So 3.9 times 10 to the minus 11 divided by 0.01. Multiply that, that's out, that's 4S squared, isn't it? So that's going to be divided by 4 square root equals S, which equals 3.1 times 10 to the minus 5 moles per liter. Okay. Just double check. Yep, 3.1 times 10 to the minus 5. All right. Now, this whole process is kind of interesting, okay, because if you ever work in a lab, if you have a real hard time dissolving something, oftentimes you'll add an acid to it and it will dissolve really well in the acid but won't dissolve in regular water. Okay, now this is a common ion effect again. Okay, now this is a little bit morbid, but that's that's Jeffrey Dahmer, right? He's a well, he was, because he's dead now, right? He was killed in the jail in Milwaukee, right? Okay, so infamous serial killer Jeffrey Dahmer, right? So what he would do, it's kind of crazy, he would kind of go to these nightclubs and pick up guys and take them back to his place, and then he'd turn them into these kind of zombies by kind of dripping kind of acid onto their skulls and things. It's totally crazy, right? And then he never got caught for such a long time because they used to dissolve their bodies, right? If you want to find somebody and charge someone with a crime like murder, you need to have a body, really. And Jeffrey used to dissolve their bodies, right? The skin and flesh and stuff's easy to dissolve, but the bones, how do you dissolve bones? Well, calcium phosphate's a bit like magnesium carbonate, okay? So we'll talk about that example, all right? Jeffrey Dahmer actually was caught because they raided his house and they couldn't find any bones. And then they looked this up on the internet. They looked in his fridge and found a few heads. So don't, if you don't keep heads in your fridge. Okay. So consider this equilibrium, right? So there's a sparingly soluble material. It could be calcium phosphate bone, right? Same idea. And it's in equilibrium with its solvated ions in very small amounts. It's a solubility product situation. However, let's say now we use HCl as a solvent, right? It completely breaks apart, right? But then H plus will react with one of the products from dissolution to make HCO3, right? So it's a bit like a buffer. It's actually going to remove stuff from solution. So if I have Mg CO3 solid in equilibrium with Mg2 plus CO3 2 minus, and I throw some H plus at it, and this works for pretty much any insoluble thing, right? That turns into HCO3 minus. That's a different thing, so that goes down, right? That means to replace this, the equilibrium moves to the right. So we can dissolve our insoluble things by adding acid to them, okay? All right, because the conjugate product, oh wow, let's not call it the conjugate, this, one of the solubility product over here reacts with the external H plus to make something new. If it's new, it's not an equilibrium anymore. Right? Okay, last page. Now this one, I'm not going to go through it now. Okay, I'm not going to go through it now. I am going to set it for some significant extra credit homework. Okay, I'll give you a couple of clues though. Okay, so a solution can, this is what they do in industry. So in industry, you'll like refine some ore and you'll typically add it nitric acid to it, and everything will dissolve, right? So you've got some Pb2 plus ions in there and some silver ions in there, okay? AgI has a KSP of 10 to the minus 17, lead iodide 10 to the minus 9, right? So what you're going to do, you're going to drip in I minus aqueous, yeah? When the solubility product is reached, right, precipitation will happen. So what's going to precipitate first? This one or this one? Well, obviously this one, right? Because the concentration of the ions to get to 10 to the minus 17, it's going to be a very small amount of I minus you add. You've got to add a lot more iodide to make this one precipitate when this is true, right? Okay, so this one will go first and this one will go second, okay? That's easy. Now, to prove it, you got to do the math, right? So work out the specific concentration of I minus needed to begin precipitation, all right? So if you can do it for both. Do it for AgI, which is an easier problem, okay? But really you should do it for PbI too, okay? So work out the concentration of I minus, set up an ICE grid, okay? Two different solubility product values for KSP. And then tell me what value I minus has to be for KSP to be reached, right? And when that happens, you get a solid, okay? So obviously this one will happen first. You have a lower concentration of I minus to make that happen. And then this one will happen second, okay? So, you know, work it through here, take a picture with your phone, send it to me as an email attachment, okay? And that's the end of the packet, all right.